UAVs for communication purposes. A study done by Eric Benelli,
Haixiao. Here is the outline of our presentation.
UAVs, a brief introduction, benefits of UAVs for communication, network and channel implications, challenges, 3GPP standards, and conclusion. UAVs, or better known as unmanned aerial vehicles, a brief introduction. The first recorded use was in 1849, where Austrians tied bombs to balloons in order to attack the Italian city of Venice. Advancements continued through the 1900s, mainly for military purposes. For some examples, they used them as aerial targets to practice anti-aircraft defense strategies and shooting. They used them as decoys to deploy in gunfights and other tense situations to act as distractions, and as well as recon drones to perform surveillance gathering, images, and intel. Today, UAVs employ a wider field of usage, such as personal entertainment, business advertising, and wireless communications. UAVs can be broken down into two main categories: mobile-enabled drones, or MEDs, and wireless infrastructure drones, WIDs. Mobile-enabled drones are the drones most people are already familiar with today. For example, the type of drones you can buy off the market for your own personal entertainment are considered MEDs, along with wirelessly manned drones that are used by businesses and the military for such use as inspection, monitoring, and surveys are also MEDs. These type of drones operate on two main link types with ground control stations: TR-3677 and application links. Wireless infrastructure drones introduce a new use for drones by using them to improve wireless and cellular network performance. WIDs are usually designed as on-demand systems. These are the type of drones that will be discussed in this presentation. There are many benefits of UAVs for communication purposes. Three of the main benefits are highlighted below: UAV-aided ubiquitous coverage, UAV-aided relaying, and UAV-aided information dissemination and data collection. Each of these benefits will be discussed on the following slides.
For UAV-aided ubiquitous coverage, the main purpose is to improve the existing communication infrastructure. It can provide quick service recovery and solve the overloaded base stations. For example, when a service area is overloaded, the neighboring UAVs can help that area to improve the communication quality.
Another key benefit of using UAVs in network infrastructures are as UAV-aided relays. UAV-aided relays provide an alternative communication path between the transmitter and the receiver. This can be extremely useful when there is no line-of-sight path available. Take the example below. Here you have the transmitting signal coming from the truck on the left and being passed through the UAVs to the soldiers on the right. The UAVs allow the signal to avoid the obstacles restricting the signal, in this case the mountains, providing a clear transmission path to the soldiers. This is essential to reducing the effect of multipath fading. Finally, UAVs can be used for UAV-aided information dissemination and data collection. In this case, the UAV is used to quickly transmit or receive data over a large number of devices, saving time, money, and manpower. In the example below, the UAV flies over a field where there are many small devices that are being used to collect agricultural data. While flying over the devices, the UAV is able to quickly communicate with them, sending and receiving important information.
The next topic is network and channel implications. For network links, there are two major types: control and non-payload communication links, which is also called CNPC links, and data links. For CNPC links, The main purpose is to achieve high operation safety. There are three major data flows in CNPC links: command from ground control stations to UAVs, state information from UAVs to ground control stations, and sense information between UAVs. The key performance of CNPC links is the ability to avoid ghost control. For data links is used for supporting the ground terminals to assign missions to UAVs. It may contain base stations, mobile terminals, wireless sensors, and so on. As for channels, there are also two major types of channels: UAV to ground channels and UAV to UAV channels. The design for UAV to ground channels is complicated due to fading. Unlike air to ground channels, people have not done the required system modeling and measurements for UAV to ground channels. For example, in urban, the signals may be blocked by buildings or affected by the airframe itself. However, compared to UAV to ground channels, UAV to UAV channels are much simpler since they are mainly dependent on LOS components. One fact of LOS links is that they may lead the upcoming millimeter wave technology to help UAV to UAV wireless backhaul to achieve a higher capacity. Although the capacity of UAV to UAV channels are also limited by multipath fading, the effects are minimal compared to other channels. UAV-aided communication systems have many benefits, but it still faces some challenges. The challenges can be summarized in three aspects: deployment, energy, and limitations in MIMO systems. For deployment, one of the most important parts is path planning. The distance between transmitters and receivers can affect lots of factors of the quality of wireless communication systems. A long distance can cause large path loss and fadings, and it will result of a low channel capacity. Therefore, optimizing a UAV flying path is an important task. However, the measurement result in path planning is time-varying. In other words, the measurement results will change as the natural environment changes, so it's hard to create an accurate system model. One solution is creating a discrete time-space, which means mapping positions and velocity information in a 3D system. As for energy, the UAV operation duration is dependent on its onboard energy. The solutions to this problem can be summarized into two aspects: energy-aware deployment and energy-efficient operation. Energy-aware deployment indicates energy replenishment. One effective way is to improve interactions between UAVs. For example, once a UAV needs to leave its serving area for an energy replenishment, a neighboring UAV can come to this area for a while during the gap. Energy-efficient operation indicates an energy management method. In this case, people need to minimize undesired energy consumptions. The last challenge is the limitation in MIMO systems. MIMO technology stands for multiple input, multiple output technology. It's widely used today due to its high spectrum efficiency. However, its application with UAVs still faces a large number of challenges. The first challenge is scattering. The scattering in UAV environment is not enough to reach a desired multiplexing gain of MIMO. Another fact is that MIMO systems need accurate channel state information (CSI) to have the best performance. However, UAV environment is a time-varying system, so it's difficult to get an accurate CSI. One solution is to use multi-user MIMO. The right graph shows a model of multi-user MIMO. In multi-user MIMO system, people divide the one receiver into multiple one single antenna users. In this case, UAVs will serve ground users at the same time, and different UAV arrays represent different received signals for different users. Thus, we can reach the desired multiplexing gain in this case.
3GPP standards. The Third Generation Partnership Project, or 3GPP, is an organization that aims at preparing specifications for mobile communication systems. 3GPP has worked on setting up a technical platform, along with regulations, to adopt the use of UAVs in cellular networks. Specifically, the three most recent releases, Release 15, 16, and 17, highlight the main requirements for UAV integration. In Release 15, the effects of servicing low-altitude UAVs were studied. Some of the results are, for low-density or rural environments, LTE performance of UEs are not significantly downgraded by UAVs. For increased density or urban environments, LTE performance of UEs are downgraded by UAVs, including interference on the uplink and downlink. These findings led to work being done on the LTE radio standards to help compensate for UAVs. Some of the work done was indication of UAV's airborne status, as well as enhancements for improved mobility performance and interference detection. Release 16 is currently still in progress, but has a completion date of March 2020. The goal of Release 16 in terms of UAVs is to find a solution for identifying UAVs that meet requirements for UAV operators, law enforcement, and original equipment manufacturers. To the left, we have an example of what this identification architecture would look like. The concept is to use control data that is transmitted by the 3GPP network between either a UAV or a UAV controller and centralized network-based UAV traffic management or UTM function. Some of the use cases being studied are initial authorization to operate UAV, live data acquisition by UTM and from UTM by law enforcement, as well as enforcement of no-fly zones and separation of UAVs operating in close proximity. In Release 17, the idea is to propose more requirements and key performance indicators, or KPIs, for UAV applications that will cover commercial and hobbyist use. Some requirements that will be documented are KPIs based on communication service, KPIs for command and control traffic, onboard radio access nodes, service restriction for UAV, and network exposure for UAV. Another main focus of Release 17 is the study on application layer support for unmanned aerial systems, or UAS. The application dedicated group 3GPP SA6 are studying use cases and requirements regarding UAS identification and tracking. SA6 is also looking at the impact on the application layer, specifically the application support/enabler functionalities of the UTM and service interactions between the UAS and the UTM.
In conclusion, UAVs provide a new look on establishing wireless networks. There are many benefits and challenges for using UAVs in wireless communication. 3GPP sets the standards that need to be met for UAVs to be integrated into cellular networks. Here are the references we used in our project. It includes the papers and the 3GPP work items.
Thank you for listening to our project.